Now that we've reviewed the theory of quantum mechanics for a single system, we need to describe quantum mechanical systems that are comprised of more than one element. Now, how do we describe that? Supposing we have a state, psi, which is an element of some Hilbert space, H1, and we have a different state of a different system, and that different system is going to live in a different Hilbert space, H2. How are we going to combine these two spaces and states into a description that describes the quantum mechanics of two interacting systems? Now, importantly, this is different to what you get when you do the same thing in classical mechanics. If I have one system in classical mechanics described by a vector, and I have another system described by a different vector, then to describe the two systems, I just have the two vectors. And so, in fact, all I need is a pair of those two vectors, and I've described my two classical particles. And indeed, any state of my two classical particles must be one vector for system 1 and one vector for system 2. That might be our first thought for how to combine two quantum systems. We'll describe system 1 by a state from its Hilbert space and system 2 by a state from its Hilbert space. The problem with that is that quantum systems can do something that classical systems can't. So my quantum system could be in state psi 1, which is an element of Hilbert space 1, and phi 1, which is an element of Hilbert space 2. And so that's a valid state, just that pair of things. But I could also have them being in a different state. And those are two completely valid states of the system. Now, in quantum mechanics, we know that we have to be able to have the superposition of these things, with some complex coefficients between these, being a valid state. So this should be a valid state of my system, because it should be an element of a Hilbert space. Now, is there a mathematical way of adding these two things such that we end up with something from Hilbert space 1 and something from Hilbert space 2? And of course, you can imagine a very simple one looking like this. Now that's achieved what we wanted, and that's taken these two states here and put them into a superposition and still left us with something in the form of something from Hilbert space 1 and something from Hilbert space 2 kind of stuck together. But it's lost something very important in the translation. In this state up here, we had system 1 in state psi 1 and system 2 in state phi 1. And so those two things were correlated. And the other state we were considering is where these two things were correlated, psi 2 and phi 2. If we come down here, those things are not correlated at all. System 1 is in a superposition of psi 1 and psi 2, and system 2 is in a superposition of phi 1 and phi 2, but there's no real link between psi 1 and the phi 1, or the psi 2 and the phi 2 anymore. And so we're not really in this superposition of these states. If we were to make some measurements on this, it wouldn't really extract anything that looks anything like that. So this idea of demanding that we have one thing for system 1 and one thing for system 2, which we get classically all the time. If I have a state of a classical system, it does. If I have two systems, one of them is in one state, the other one's in the other state. And that's fine for a classical system, but for a quantum mechanical system, we want correlations, like this, but we want the correlations themselves to be able to be in a superposition. And what we've got here is this kind of sum is a direct sum, where you just add the dimensions of your two systems. And what we really need is we need a tensor product. So in something like classical mechanics, we have a single value for the state of each system individually, and you're just adding them together. The total vector space that you get has a dimension that's the sum of the dimension of each of the original vector spaces. If you have to account for all the possible correlations that you might have between the two systems, the final vector space you get has a dimension that's the product of the dimension of each of the original vector spaces. Now you may have learned about tensor products in the context of tensors, either in classical mechanics or special relativity or in a mathematics course, but we'll cover all the basics now. So supposing you have a basis for the first Hilbert space, and a different basis, of course, for your second Hilbert space, then the basis for the Hilbert space is the tensor product of H1 and H2 is the tensor product of each of these basis vectors. That may seem a little bit circular, but actually once you've specified the basis for something, you've pretty much defined everything about it. So it's a normal vector space, and each of its basis vectors are indexed by a j and a k. Let's look at some of the properties of how we deal with these things. So supposing we had two states as we had up here, we might have psi had to be expandable in terms of its basis, of course, so these are just a bunch of coefficients. And same with phi, except it's in a different basis. Then if we take the tensor product of these two states, tensor products are linear in everything. We can take the sums out of both, and we can take the coefficients out of both. So we've got both sums out the front, both complex coefficients out the front, and these are our basis vectors of our combined Hilbert space. Now, because this particular state could be written as the state of one system tensor product with the state of the other system, this is known as a separable state. And note that if I wanted to define a completely general state, then I'd have coefficients here. This is a complete basis, so I'd have an arbitrary set of coefficients here, and an arbitrary set of coefficients would be a function of j and k together. Whereas here we have a separable function. So a separable state has, at least in some basis, a separable set of coefficients like that. But for two quantum systems that can be interacting, then there exist states that are not separable. For example, let's take a very simple example of two spin half systems. So each system can either be spin up or spin down. What about this state? That state there is very explicitly, you can see there's a correlation in the spin. So both spins are up or both spins are down. And so the state of one depends on the state of the other. So that can't be written in this kind of form here, where we have the state of one system tensor product with the state of the other system. And so this is known as a non-separable state, or also more commonly an entangled state. An entanglement is a property of quantum systems that generates a lot of very interesting and strange behavior.